Welcome to Module 6 of the Insight and ProWiFi training course. In this module, we'll focus on how to configure and customize the Wi-Fi settings of our Insight deployment by explaining fundamentals such as frequency, channel, signal strength, modulation, roaming and data rate. The placement of access points is also an important consideration thanks to the array of different environments depending on the project, so we need to explore this as well. But before we crack on, let's once again have a quick reminder of the overall objectives for the course. To begin with, it's important that we understand some basic terminology to make sure that we make intelligent configuration decisions over guesswork. And we'll begin with signal strength. Now, we're all familiar with that rudimentary strength indicator on our computers and mobile devices. But what exactly is it referring to? Well, Wi-Fi signal strength is measured in dBm, or decibel milliwatt, and it's displayed as a negative value. It's displayed in dBm because really the most accurate way to express Wi-Fi strength is in milliwatts. But because Wi-Fi has really low transmit power, we would end up with displaying the strength with loads of decimal places using milliwatts. 1 milliwatt, for example, is 0 dBm. So that means that minus 40 dBm would equal 0.00001 milliwatt. So it's far easier to refer to it using dBm. Under normal circumstances, signal strength close to a wireless access point would be around minus 30 dBm. However, we also sometimes measure the signal strength by RSSI, or Received Signal Strength Indication, which refers to the signal strength being received by the antenna of a wireless device. Wi-Fi uses 3 frequency bands: 2.4 GHz, 5 GHz and 6 GHz. Each of these bands are just short sections of a huge frequency area, as we can see here. The rules and regulations as to which channels are permitted for private wireless communication varies between countries and regions. However, universally, these channels are all contained within our 3 frequency bands. We'll come back to this a little bit later in the module. Finally, interference refers to disruptions or noise which can destroy wireless signals by consuming airtime in a Wi-Fi area. Sources of interference can often be neighbouring networks, multiple networks in the same house, microwaves, baby monitors and loads of other wireless devices using Bluetooth communication. Today, interference is primarily an issue on the 2.4 GHz frequency band. However, due to the rapid increase in wireless technology, we're also seeing a lot more impact on the 5 GHz frequency band. Something, again, which we'll be able to alleviate using the next generation 6 GHz devices. We're able to select which bands we want to use in NETGEAR's Insight remote management software by navigating to Organisation, Location, Wireless and SSID. In the same screen, we can select devices to enable the radio and set the radio mode, channel width and output power of each wireless access point. The 2.4 GHz Wi-Fi band has been widely used for radio wireless local area networking devices which are based on the IEEE 802.11 standards since the early 2000s. It offers 14 frequency channels between 2.401 and 2.484 GHz, with 3 non-overlapping 20 MHz channels in the US and the EU, those being channels 1, 6 and 11. Non-overlapping channels refer to complete frequency channels within the band,
which can be used exclusively without having other non-overlapping channels impeding them. Users can choose to double the size of a single channel to 40 MHz to increase throughput on certain devices in less crowded environments. However, in crowded areas more susceptible to noise and interference, a single 20 MHz channel will be more stable. Finally, as we alluded to earlier, the 2.4 GHz band unfortunately shares the same space as many other radio devices, which can interfere greatly with Wi-Fi traffic. While 2.4 GHz is able to send packets further than high frequencies, this is often countered by interference from all these other devices. From around 2007 onwards, the 5 GHz Wi-Fi band was made widely available alongside the 2.4 GHz band to accommodate the growing number of wireless host devices being introduced to both the commercial and residential technology spaces. This is a higher frequency, therefore it's able to transmit data quicker than 2.4 GHz, however, not as far. Again, users are able to determine the width of each channel with the addition of two larger choices, those being 80 MHz and 160 MHz, which both work well in less congested areas. And while interference from other devices utilizing the same radio space is possible, there are less of those devices likely to interfere with the signals. The latest addition to the Wi-Fi spectrum used for data is the 6 GHz band. Exclusive to the newest Wi-Fi standards, Wi-Fi 6E and Wi-Fi 7, 6 GHz provides the least coverage but transmits data at the fastest speeds of all three frequencies. The 6 GHz wireless band was introduced with the Wi-Fi 6E standard and is exclusive to devices which support Wi-Fi 6E and newer standards, including Wi-Fi 7 and successive future Wi-Fi versions too, which means that on 6 GHz the Wi-Fi network doesn't need to slow down to accommodate legacy devices. The 6 GHz band also supports almost twice as many channels as 5 GHz. In short, fewer devices offering more spectrum and more bandwidth means less interference and network congestion. EIRP, or effective isotropic radiated power, is how we refer to the output power being radiated from the isotropic antenna contained within a Wi-Fi access point. And we measure this power in dBm, as we mentioned earlier in the module. These U-NI or uniband numbers refer to the unlicensed National Information Infrastructure radio bands, which define the power limits for, amongst other things, wireless communication devices sharing IEEE standards. Remember that the higher the frequency, the quicker the speeds, but also the higher the power output potential. If we go back to our overall radio spectrum, we can see that at the top end, where cosmic rays live, while the coverage is tiny in comparison, the sheer amount of power emitted at the frequency can be deadly. Why do you think the operator runs into a protective booth whenever you have an X-ray? Depending on location, 6 GHz access points can operate between 30 and 36 dBm EIRP, or a maximum spectrum density of around 5 to 23 dBm per megahertz, based on whether the access point is for indoor or outdoor use. They all have to operate under the control of an automated frequency coordinator, or AFC system, which assigns a list of frequencies to the access point based on its location. This mitigates the interference with incumbent systems. It's pretty technical stuff, especially as the frequency band increases, but most of these considerations are already being determined and managed automatically by Insight and the access points themselves. In the context of Wi-Fi, roaming refers to the way a host device connected to one access point moves to another access point on the same network. The host device is associated to the same SSID or network name, but the unique MAC ID or BSSID address for each access point will change, and this needs to be managed. The host device itself will have a minimum signal level required to maintain its current connection, and we call this the trigger threshold. Once this threshold has been crossed, the host device will then immediately connect to another device which exceeds this trigger threshold. This reconnection takes place almost instantly in 5 GHz and 6 GHz networks, thanks to a small overlap to allow the host's RSSI, or Received Signal Strength Indicator, to determine which wireless connection to switch to beforehand. However, this often results in the client remaining connected to the current BSSID for longer than you may expect.
You'll find the fast roaming settings in Insight at location level in Organisation Location Wireless Settings Fast Roaming. Opportunistic Key Caching, do you like that? Or OKC, is a fast roaming solution which is a predecessor to the 802.11r fast BSS transition, both of which being mechanisms which significantly reduce the time taken to switch from one BSSID to another. You can enable the OKC fast roaming feature here, which will also avoid captive portal reauthentication. To set roaming at the SSID level, go to SSID, then Settings, and under Radio Settings, enable 802.11r to allow the initial handshake with the new access point to be carried out even before the client roams to the target access point, a process that we call fast transition, or FT.
Instant Wi-Fi, sometimes called Auto Radio Resource Management, or RRM, uses Wi-Fi radio statistics from each access point in a network location to calculate the best channel and best transmit power for the access point. Clients should only see one strong signal access point when roaming, and Insight devices can trigger instant Wi-Fi based on an increased amount of neighbouring access points, noise, or load on the operating channel. You'll find these settings in Organisation, Location, Wireless, and Settings, and the Insight admin can make further changes to each channel to optimise immediately based on a schedule or from device-triggered events.
The advanced rate selection in Insight, or advanced rate control in the user interface of each access point, allows you to control further parameters relating to the minimum Wi-Fi rates for your network SSIDs. If you're using IGMP for multicast streams, Internet Group Management Protocol, your access point defaults to automatically transmitting all multicast frames at 1 megabit per second. That's on the 2.4 gigahertz band, and 6 megabits per second on the 5 gigahertz band. However, for better multicast performance, you can try setting a higher multicast Wi-Fi rate to improve the overall wireless performance, therefore reducing the amount of airtime used for multicast frames, and that leaves more airtime for other data. Enabling the Set Minimum Rate Controls checkbox in Insight, or the Rate Control checkbox in the user interface of the access point device, presents the density level slider, allowing you therefore to alter the beacon rate and the minimum legacy rate of your Wi-Fi network. What do they mean, Matt? Let me tell you. The beacon rate refers to the Wi-Fi rate used to broadcast the SSID to wireless client devices or hosts, and the minimum legacy rate is the minimum Wi-Fi rate that a connected host device can use. In wireless networking, we refer to something called the MCS index, or Modular Coding Scheme Index, to give it its full title. Now, the MCS index is an industry metric based on several parameters of a Wi-Fi connection between a client host device and an access point. These parameters include data rate, channel width, and the number of antennas within the device. Setting higher minimum Wi-Fi rates and minimum MCS indexes may improve your overall network performance in a number of ways. For example, it can prevent wireless devices from connecting at lower Wi-Fi rates, which might use excessive airtime. It can also force an access point to use higher Wi-Fi rates for management and control frames, such as beacons. And again, that would leave more airtime available for other data. It can also deny connections from wireless clients using lower throughput modulation, because these clients might be using excessive airtime due to their lower Wi-Fi throughput. If in doubt, of course, it's always best to let Insight manage these parameters automatically. However, in certain environments, it may well be necessary to alter these settings to optimize a particular network. Finally, as is the case with any network, a clear networking plan is essential when specifying, implementing and troubleshooting the network in future. There's a lot of truth behind the phrase failing to plan is like planning to fail. NETGEAR are on hand to support you at the early stages of designing your wireless local area network, to assist you with specification, implementation, any complications which may arise, and connectivity requirements between the network endpoint devices. Questions will invariably arise when you need to deploy Wi-Fi in a new location. How many access points will I need? How much is it going to cost? How many switches do I need? Well, NETGEAR provides a free professional service to generate remote site survey reports relating to all aspects of Wi-Fi planning, including heat maps to illustrate the Wi-Fi coverage and signal strength. The Wi-Fi plan varies considering a number of key factors. They depend on the size of the area, the building materials used, the position of the access points, and the number of users, for example. Just send an email to ProWiFiDesign@netgear.com. That's ProWiFiDesign@netgear.com to connect with the team and make sure your future deployments are done right first time. That brings us to the end of this module. We've covered a lot here, haven't we? Just make sure you take the short quiz to check that you've understood the content we've been discussing. Recap as many times as you need to gain more confidence. And when you're ready, I'll see you in the next module.